Okay. So Varisha, we did it till like the Archimedes principle, and we also proved it. And now we're going to look at some conditions here. So, so we will learn about these three conditions. One of them is that if the object which is submerged in the body basically has no acceleration, and then if there is an object which is basically moving down. Oh, in fact, let's talk about it has no velocity. And then one object which is moving up. So basically what it means is that if something isn't moving, the weight is going to act downwards and the upthrust is going to act upwards, and the weight will be equal to upthrust, and we can always say that the object will float. Okay. Now, if it is moving down, that would mean that the weight is downwards, like it is, but the upthrust is upwards. The upthrust will not be the same as the weight, but also there's going to be another force, and that force is going to be drag acting as well. And the drag would be such that basically this weight will be the largest force, and upthrust will try to balance it out, and the object will be falling at terminal velocity. So this object will sink. Do you understand, Varisha?
Yes.
Okay. Now, then we are going to look at the last one. And when something is rising like this, right? So it means the upthrust will be the largest force this time. The weight is going to be less than that, and that would cause the drag force to act, downwards. And when you add both of them, you realize, okay, the upthrust will be equal to weight plus drag, and the object will rise. And that's very important to understand. Okay, is it clear?
Yes.
So the weight is here regarded as W, upthrust I've written as U, and the drag force, which is the opposing force, as D. We will talk about the drag force in a bit, okay? Alright, you can copy this down then.
Yes.
Okay, Varisha, done. Should I move forward then?
Yeah, I'm good.
Okay, second please. So now when something is like Varisha moving, right? So we can always, we can do basically a question here, and I just show you what basically I mean, and how would we look at the questions at this point. So suppose it says uh-huh, a giant garbage barge on a river is 60-meter long and 10-meter wide. What depth of the hull will be underwater if it and its cargo oh, have a combined mass of I guess 1500000 kg. Is it clear, Risha? Say the density of water is going to be 1000 kg per meter cube, like that. Now, if something is floating, you know, so this is, let's suppose this is the water, this is the surface of the water, and if something is floating like this barge, so we're taking it as a square one, a rectangle one, like this. So we know that we want to find this height that is underneath this, I mean the one that is submerged, and because of that there will be an upthrust here and the weight is going to be down, right? Do you understand, Varisha?
Yeah.
Okay. Now, so basically, we know that in the case of floating, like we said earlier, the equation is like the weight is equal to upthrust. So we can say, okay, case of floating, we can write weight is equal to the upthrust, and that's how it floats. Now, because weight is mg, and we can find weight as 1500,000 kilograms multiplied by 9.81 is the g. So that would be around 1.47 times 10 raised to power 7 newtons. Okay, Varisha?
Yeah.
So this means that the upthrust then also is equal to 1.47 times 10 raised to power 7 newtons. Now, we know that upthrust is given by rho g and the change in volume that is caused by that. So what you're going to do is, first of all, we try to find the volume, right? So upthrust we know is 1.47 times 10 raised to power 7. The density is 1000. The g is 9.81. And about the volume, so length it had was 60. So I'm just taking volume and we're writing here length, width, and height. Okay, length is 60, width is 10, and height, let's say this h that we marked on the drawing, 12. So when you find this out, this h is going to be equal to 2.5 meters, and this means that this is 2.5 meters inside water. Understood? Is it clear?
Yeah.
Good, that's very good. Can you write this down, please?
Okay, I'm good.
Okay. Okay. Now, so then we try to move. Then when it is moving, so what happens then? Okay, let's talk about that. So whenever something moves under flow in fluid, so there is basically two kinds of flows. So we're gonna look at the fluid movement basically. So the kind of flows that we have are, number one, laminar flow, and number two, we have turbulent flow. Now the real basically difference between laminar and turbulent flow is that laminar flow is also known as streamed streamlined flow, and usually occurs at low velocity there are no sudden changes in velocity, and particles flow in almost straight lines in their own paths. Okay? So why do we call them streamlines? Because basically, if the fluid is flowing inside maybe a pipe or something, so they just flow like in their own paths like this, very nicely. If you notice, they're much slower, like they're faster at the center and slower at the ends, and that is because this whole thing is inside a pipe, okay, Marisha? And because it is inside
Yes.
the pipe, basically the particles get a little bit friction from the walls itself, which makes them slower. So at low speeds, they do not try to just mix up because of that, right? So the direction and speed might differ a little bit, but that's not a big deal, right? So that's fine. So basically, the lines that you see, lines of laminar flow, are called streamlines, and that's why we call it streamline flow. Okay, is it clear, Marisha?
Yes.
Now, turbulent flow basically, usually almost every time, basically, occurs at higher speeds there are sudden erot- erratic and chaotic changes. All right. Speeds vary at larger scale, which means they're like very turbulent, and causes somewhat like, I would say, uh, swirl of eddy or I'll say swirl of eddies. Okay, I'll just explain it just now what that means, okay? Now, let me tell you this. Now, what happens is that, so in the same pipe that we talked about, they basically try to push themselves in the middle, right? Because the bottom ones are basically a bit, have the near the wall, they're like higher friction, so the difference between velocities is too great, and basically that causes a very turbulent sort of movement within the pipe, which basically cause the water to just be very, very, erratic in its movements. Understood? So the movement is because we just need to remember, I'm just going to write it here, that the friction between outermost layer and the pipe wall means this layer will slow down the end ones, right? The bendmost. Slow down the most effectively. And the inner layer, which is not directly in contact with the wall of pipe, is faster. Okay, that's fine. This causes a significant difference in flow speeds, which may hinder the path of particles moving along. Do you understand?
Does this not apply to laminar flow?
It does. Like what I'm saying is, laminar flow, you see, if this was like, imagine if this was moving at 5 meters per second, the last one would move at maybe 4.5 meters per second. So there's not much of a difference here. That would not cause it to redirect itself. Do you understand? But at faster speeds, like if this is like 25 meters per second, and then they're like these ones at the end, they move at like 5 meters per second. That is a huge difference, and that would cause them to, try to indulge into the middle one that causes turbulent flow. Do you understand?
Yeah, okay, got it.
Now, one of the reasons why today the aerodynamics of a car is so important, and we do take that in consideration, is because if a car is designed like this, right? It's low to the ground and it's streamlined, right? So when it's moving in this direction, the lines basically tend to flow, the air lines tend to flow rather smoothly over it, which causes less force, or the drag coefficient basically lessens. Do you understand, Varisha?
Yeah.
But what if the car is made like this, a box type, and there is no streamlining done, and it's a poorly designed car? Then what happens is that the air basically tries to move turbulently across it. Do you understand? Like this. And at the back of the car, they just try to, because low pressure happens here, so there's the region of low pressure. And because of that, the air basically swirls like this and forms eddies. You get my point, Manish?
Yeah.
So definitely at higher speeds, the car that's going to be performing much better with required less power would be the one that's more streamlined, right? Okay, so you know the definition, you know how it works, right? Uh, that would be it. Is there anything you would like to ask? Please let me know.
No, I'm good.
Okay, so Varisha, I'm just gonna show you one thing very important, right? Basically, I am a car enthusiast, and I'm gonna show you something like there's this car that's called ah damn. It's called Lucid Air. Okay, so the name is like you might. It's an electric car that's there to counter Tesla. And Lucid Air basically is designed in such a way. I'm gonna show you the shape of it. Lucid Air streamlining. So they have, I will show from the back, right? So they've tried to, make it so sleek, and the curves are like made like this, so that it feels very small drag coefficient itself, just like this. You see the the shape of it? Do you understand? In
Yeah.
fact, in fact, there's another car like that's basically a hybrid car. That's basically called Honda Insight. I just want to show you the latest generation. Okay, so Honda Insight, the latest one, I don't know why it's not showing that, but they have redesigned like this. Do you see that flap on the ugly flap on the rear tire?
Yeah.
The reason is they don't want the air to basically bend and go towards the tire. They just want to pass, like it should slide past the back tire like this, so that the streamlining is not affected. Do you understand? And they can't do it in the front wheel because it has to turn. That's why it can be done on the rear wheel. So that's how they design and they try to do it this way. Okay. So Varisha, I think we should stop here because the next topic I want a full class for that, the drag. Okay. And I will see you then tomorrow, same time. Bye. Have a nice day.